Today we're going to talk about Gauss's law. And so we'll start out with what is Gauss's law. So Gauss's law is a general statement about the nature of electric fields. It's more fundamental than Coulomb's law and is the first of what we'll later call Maxwell's equations, which are the governing equations of electricity and magnetism. So Gauss's law says that electric flux through a closed surface is proportional to the amount of charge enclosed within that surface. And it's going to end up being a very powerful tool for us to calculate electric fields. I just want to point out that for me, this was the most difficult concept I've seen up to this point in physics. Not to scare you, but just to be real clear. So this is tough stuff. We're going to unpack it over the next couple of lectures. But let's start just with the idea of conceptually, the concept of what's going on here. And so what we're saying with Gauss's laws, we're going to find out that if I know the electric field on some surface, so here we have this nice cube. If I know the electric field on this cube, I can tell a lot about the charge inside. And so here, the electric field on this cube is all pointing outwards. And so inside that box, you can say there must be some positive charge. In a similar sense, if I've got these electric field lines going in, I can argue that there's some negative charge in that box. And finally, in the case here, the electric field is going through the box and it's not affected at all. And so from there, I can say, just reasonably looking at this thing here, that I don't think there's any charge inside that box at all. So that's the basic idea of this. And so now we're going to go through and try to make this a little bit more quantitative. But let's start here. So here we have this picture to kind of give you the flavor of this. And so we're looking at this two-dimensional E-field line diagram. Part of it is hidden from view. If the object in the top left, which is this object here, if this object is 1 coulombs, and you can see the number of lines coming on and going off, how much charge is in that other object? So go ahead and pause here and think about this and see what you're thinking. All right, so let's go through and do this. So I got the answer here to be -1 coulombs. And so hopefully that makes some sense to you. Let's talk about this. If I look at this one here, I counted 12 lines coming off of it. And so I'll say positive 12 is the number of lines leaving that surface. If I look at this one over here, by the same token, I had negative 15 lines. So there was 15 lines leaving. And then there was 15 lines coming in. So we call those negative. And then 3 lines leaving, which gives me a total of -12. And so the way we think about it is, again, lines leaving the area tells us that that's a sort of indication that there's a positive charge, and lines coming in is indication that there's a negative charge. And so they're the same number, equal and opposite. And so my guess is that it's -1 coulombs. And if you look at, here's the actual picture that we use to make this from, and you can see that it's true. So 1 coulomb on the left, and that other one has a total of -1 coulomb. Now it's really important to show here that we didn't know anything about the actual distribution of it. It turns out that it's a -4 and a +3. But again, we can learn a lot about the charge inside knowing something about the electric field lines on that surface. So a couple definitions, again, to help us get this more quantified. A Gaussian surface. A Gaussian surface is the surface we're talking about. It's a closed surface through which an electric field passes. And the one key thing is that this is an imaginary surface. There's no charge on it. It's not a charge. It's just this imaginary mathematical thing that we use to help us with Gauss's law. It's not anything physical. It doesn't add any charge or take any charge away or block charge or anything. It's just a completely imaginary surface. The next thing we need to talk about is flux. And so flux, we're going to define it in a second, but the sort of general idea you can get is that if we think about the volume of air flowing through a loop, and so here we have a loop and air flowing through it. The flow is maximum when the loop is perpendicular to the airflow, and it's a minimum, it's 0, when the loop is parallel to the airflow. And so this is the way electric flux is going to work. We're going to have these surfaces, and if the electric field is sort of piercing through it, we're going to have a large amount of flux. If the electric field is sort of passing to the side of it, like in this picture, we're going to have 0 electric flux. And so the way we can define electric flux is it's the number of E-field lines that pass through a surface. And so you look at this picture here, there's a bunch of E-field lines and some surface with area A. To actually calculate that mathematically, In this case here, so we're sort of talking about two different cases. This case is the case where electric field is normal to that area surface that we're talking about. If that's the case, then it's just the E field times the area. That's the easiest case. It's also the case that will probably happen the most common. Okay, so I think it's really important just not to forget about that case. But what's really common in Gauss's law is to get so worried about everything, as it is kind of confusing and mathematical, that you sort of miss the easy parts of it. And so that's really something to really take care of or to think about. The more general definition of flux would be in a case like this, where the electric field isn't piercing completely through, like in this picture at 90 degrees, where it's at some different angle. And we define that as being the flux equals E times A times cosine theta, where the theta is defined as the angle between the electric field and our normal vector, which our normal vector is always 90 degrees to our surface. And so this is the more general definition. Note that that definition, if we use it on the top one, gets us the same thing. So here, EA cosine of the angle, well, the angle is between the normal and the electric field. If I drew my normal vector here, it would be pointing up, again, perpendicular to the surface, and so the angle between those would be 0, and so it gives me that same EA. So this is the more fundamental. It works out to be the same in that case, but this is so important that I like to sort of talk about it individually. So let's try an example here. This one's kind of tricky. If you get this, you really have this idea down already. So electric flux through the shaded surface is what? So let me just sort of draw, this is, a lot of times with these pictures, it's just visualizing it can be the trickiest part. But imagine I'm looking straight down this surface like so. So here's the surface. The electric field lines are coming through here like this, and I want to find the flux through this shaded surface, which is this one right here. So go ahead and stop here and then try to think about this and see what you can come up with, and we'll talk about it in a second. All right, hopefully you get C. So I got answer C here. And let's go through and sort of talk about this. So here's my picture. All right, and now let me just draw my electric field lines with a different color. So electric field lines are going this way here. And my electric field in this case was 100 newtons per coulomb. All right. And then maybe I'll get even another color here to sort of draw the other thing. So here's the angle 20 is this angle in here. And so now what I want to do is I want to draw my normal vector. Here's my normal vector. This is 90 degrees to the surface. And so my definition of flux, the way we just described it, would be the electric field times the area times cosine of that special angle, which is this angle right here. So now for us, it's a matter of finding that angle. It can be a tricky, like in this case, it's not super easy. So what I would say is this would be my angle 20. Hopefully you agree with that. If this angle here is in fact 90, then this one here would have to be 70. So lots of different ways to kind of calculate that. If it doesn't really matter which way you use, as long as you have one that works. And so then in that case, I got 100 newtons per coulomb for the electric field. My area looks like it's 2 times 2, so 4 meters squared, and then times cosine of 70. And so that would be that, and then the answer we got was 400 newtons per coulomb meters squared times cosine 70. And we should probably just state that the unit of flux is electric field times area, and so it is this thing, newtons per coulombs times meters squared. So stop and review this if it didn't work out for you, but let's move on. So this definition of flux can be summarized into an equation that involves the dot product. And so we've all seen the dot product, right? So the dot product is the E vector, in this case, electric field vector dotted with our area vector. And of course, what does that give us? It gives us that same definition of EA cosine theta. And just real quickly, hopefully you can see that what happens is again, when that theta is 0, this gives us sort of our maximum value, just E times A. When that theta is 90, it's going to give us 0, right? And so basically this angle is a way to account for sort of basically how aligned that area vector is with the electric field. And then just finally, just to reiterate, so if I have some surface, this area vector, which we also sometimes call the normal vector, again, is just the one that points 90 degrees to the surface. And so my electric field, I'm always interested in the angle between the electric field and that normal vector. So that's what we always are going to call our theta there. So that's our normal vector, and here's my electric field vector. Now, we just talked about the flux through a flat surface, but we'll spend a lot of time looking at the flux through curved surfaces. And when you do that, you end up using some calculus. And so here's a nice curved surface we have written over here. All right, and what we do is we basically just break our curved surface into many small pieces of area delta A. And think about the electric flux through each small piece as the electric field dotted with the vector of this delta A, this normal vector pointing out from that surface. And what we do, like in calculus, we basically add up all the different elements of this. And this is a surface integral. If you're like me, this is probably the first time you've seen a surface integral. Maybe you've seen other ones, and that's great, all the better. But I think most of us, this is probably the first time we've ever seen one. The good news is you're almost never really going to actually use calculus here. Okay, so because in most of these situations it's just kind of a pain, and really the sort of beauty and power of Gauss's law is going to come in the special cases where you don't really have to use the calculus there. But you could do that. If you had the electric field defined on this surface, you could split it up into little tiny pieces, and by integrating add up those little tiny pieces. But what's going to happen to us is we're going to be very interested in two kinds of surfaces. The first is one where the electric field is always tangent to the surface, like in this case here. Okay, and so if the electric field is always tangent to the surface, then that means the actual number of lines going through that surface is 0. Right? So E dot dA, the electric field dotted with the little tiny area piece, is always 0. And so you're always going to have the total flux being 0. Again, you never want to forget, the idea that what this means, this idea of the flux is how many field lines are going through the surface. In this case, there's no field lines going through the surface, and so the electric flux is 0. The other situation is when the electric field is perpendicular to a surface, like in this picture here. Right? And in this case, the electric field is always constant, right, and always 90 degrees to the surface. And so that's going to be a case that we're going to be very interested in. And you can kind of go through this sort of sequence of events. You can say, okay, so our definition is E dot dA, this integral. Now here, since E and dA are perpendicular, then that cosine of the angle, so technically I would write this as an integral of then E dA times cosine of theta, but theta is 0. This becomes E dA. Furthermore, it's a case where the electric field can pop outside its constant, so E dA, and then I get just E times A. So here I have a curvy surface where the electric field is everywhere perpendicular and has the same magnitude. If that's true, then my flux, this really nasty, scary-looking integral, is just the electric field times the area. And the good news is the majority of cases that we're going to do are going to be looking at just this particular situation. So that's reassuring. Okay, so let's just do some conceptual ideas here just to kind of reiterate. So here we have two surfaces, A and B. I want to know which surface has a larger electric flux. So give this one a go, and we'll talk about it in a second. All right. Now, hopefully you got that surface A has more flux. Again, this is a tricky one, right? So what's happening here is the surface A is closer to the charge, so the electric field there is stronger. You can see that in the fact that there's more, the density of electric field lines there is tighter together than at point B. But there's also this effect that at point B, the electric field lines are sort of more perpendicular to the surface. But this is where it's important to remember that the flux is measuring the number of electric field lines going through the surface. And so if you look at A, there's more electric field lines piercing through that surface than there is at B. Let's look at another one here. So now, what is the total electric flux through this Gaussian surface? So here I have some charge that I've set up inside here. So this is some charge inside here, some positive. And I've set up this, again, this imaginary surface outside of here. And we've set it up concentric to the charge. So if you look here, the electric field is always 90 degrees perpendicular to the surface. And so what is the total electric flux through the Gaussian surface centered around a positive point charge? And so here we're using this as this surface has a radius of r. And so think about this one, and we'll talk about this in a second. Okay, so this is like that case we were talking about before, okay, where you can say that basically this is going to just equal the electric field times the area, all right? Because again, the electric field is always perpendicular, so the cosine of theta becomes cosine of 0, which is 1. The electric field pops out in front of there, and you're just integrating over the area. Okay, and so for us, that would be E times 4 pi r squared, right? If you just remember the area, surface area of a sphere, so this is a sphere, this Gaussian surface, is 4 pi r squared. So now we're ready to define Gauss's law, and Gauss's law is written out this way here. So what it says is for any closed surface, any closed Gaussian surface, the net electric flux through the surface, which we've sort of looked at trying to calculate a little bit, is equal to the charge enclosed times or divided by this epsilon naught constant. So that's just basically a proportionality factor. And so this result is known as Gauss's law. And so this is what we're going to spend, again, the next couple of lectures discussing. And so I thought we'd start here with this first clicker question. So we have a cylindrical piece of insulating material is placed in an external electric field as shown. The net electric flux passing through the surface of the cylinder is what? So what's the net electric flux passing through this cylinder? So think about this one, and we'll talk about it in a second. All right, and hopefully with this one, you got 0, right? So if you look at this case here, the number of lines leaving is equal to the number of lines entering, which is our conceptual definition of the electric flux. So it equals 0. And according to Gauss's law, this is also helpful because in this case here, hopefully you can see that these lines are caused by like a positive charge that probably lives somewhere over here or so, right? Maybe I'm off a little bit, but it's some positive charge over here that's going to create these lines like this. And so there really is, you can see here, physically, you don't see any source of charge inside this surface. And so this is a case where you can kind of, hopefully see how this Gauss's law works in a case like this. So the electric field lines, the same coming in or the same coming out, right? So there is no total flux, and what that means is there's no charge inside. And so I think it's a pretty decent example conceptually of Gauss's law. So we'll stop here for this first one. So this week and go through and ask questions on the pre-class questions because I'm sure you're going to have them. And again, remember that probably everybody does. Like I said, this is a really tough concept, and we'll pick this up and continue this.